Welcome, everyone, and hello. You're joining Brainome for our very first webinar. This is Core Tech 101, a conceptual overview of the mathematical and algorithmic innovations that we've put together for you to promote a revolution in machine learning. I'm going to encourage you to put your questions in the Q&A channel throughout the presentation. And I'm Lynn Chase, and I'm your host, and I'll be making sure that your presenter, Gerald Friedland, sees those questions and can address them before the end of the webinar. Today is Core Tech 101, a conceptual overview, but it's the first in a series of 3 Core Tech webinars. If you're really interested in all the math and the detail of how everything works, you should come back next week to Core Tech 201, and then again for Core Tech 301, where we'll go through a bunch of cool examples that show off what's going on underneath the hood. There's also a parallel webinar series going on starting on Thursday about the benefits and applications of using Brainome's Dimensions software. And we're going to kick off this week with a presentation on how to superpower your data prep using Brainome's Dimensions. For more details on all of this and to sign up for any or all of these webinars, you can go to the URL listed here, which is on our webpage, brainome.ai. Now I'd like to introduce Gerald Friedland. Gerald is going to be our presenter today. He's the CTO at Brainome and is also an adjunct professor in the Electrical Engineering and Computer Sciences Department at UC Berkeley. Before that, he was at Lawrence Livermore National Lab and at the International Computer Science Institute at Berkeley. His work focuses on signal processing and machine learning. He's published more than 250 peer-reviewed articles in conferences, journals, and he's also published 3 books. Gerald received his doctorate, summa cum laude, in computer science from the Free University in Berlin in 2006. So there's your introduction to our fabulous speaker. Gerald, take it away.
Thank you so much. And welcome everybody and to this course series. This is obviously the first time we're doing this, so any feedback is greatly appreciated. And I'm very excited to just give you a brief introduction about how our system works and what we do differently. And to start, we need to talk about how is machine learning done today, right? So the state of the art is that you have some data that you think you can build a predictor on. And so the way this works is somebody chooses some model, maybe a random forest, maybe a neural network, maybe, some combination of stuff. And ultimately, so we take the data, we label it. So what we're talking about, by the way, today is all about supervised machine learning. So we label the data, and then we put this into a machine learner. We hope that this is the right choice. We tune the parameters, and we play around until we get basically some high accuracy. So we have some error metric that we want to match, right? So we get some high accuracy on the training data, but we also get some high accuracy on some held out data. So basically we say, well, prediction works if the prediction actually works also on data that the machine learner hasn't seen. It's not the training data. And it's very similar to children taking a test, right? So you teach them something and then you give them a test of stuff that's not verbatim what's in the what has been taught, but then hopefully the children can still do that. So that's the whole idea behind that. So basically have a training set and a validation set. And then once you're basically saying, okay, I have high enough accuracy on this validation set, then people either go and, in the academic world, you go and do an external evaluation, for example, benchmarking. I worked a lot with the National Institute with NIST on standards and technology, because they had a lot of sort of worldwide evaluations where you then test your models for real. Or you don't have that and it's an industry, then in industry you go and just use the models and hope they work. And of course, then we have the horror stories of the autonomous car not stopping at the stop sign and so on. And these kind of things happen. So ultimately, if we summarize sort of how measurements work today in this scenario, we basically have three main ones. We have accuracy, which is nothing else but the number of correctly classified instances or the number of correct predictions divided by the total number of, predictions that need to be made, or the total number of instances. And of course, if you multiply that by 100, you get a number in percent. That's accuracy. There's obviously other metrics like word error rate or ROC curves and so on and so forth, but they all ultimately come down to accuracy. And once you have 100% accuracy, by the way, you don't need any of these metrics because you could just correct. Um, Now, what we have a vague notion of generalization. The notion of generalization is that we actually say, well, if on that validation set you have a high accuracy, then we generalize. Okay, and the problem is also there's a choice in validation set, like how similar is it, and so on and so forth. All of this undefined. And they say, well, maybe we take 10 choices, 10 guesses on that and do 10-fold cross validation. Yes, it's a method, but also it's just sort of a band-aid for the actual problem. And then we have a notion of model complexity that is very interesting, because usually it has to do with, oh, deep learning is better than shallow learning or something, right? So the number of layers or the number of parameters in the model. And right now, the idea is that the more parameters we have, the better, right? So GPT-3 is this huge model, and of course, we are bragging about how big it is. And so here's what's interesting. What we don't have is any kind of measurement before we actually build a model. And that is something that sort of it bugged me, because I was like, okay, before I build a kitchen, I measure it out, and then I put my stuff in the kitchen. And before I build a car, or before I build bridge, or before I build a ship, or whatever, any engineering needs to do measurements before we build something and not after the fact. And now you could say, okay, but this is machine learning. Well, the point though is I tried to answer at some point one simple question. And this was doing my work at the university, where basically my students wanted to do deep learning experiments, and I went and tried to get free cloud time from one of these providers that obviously are very university friendly in the sense. But they asked me one simple question. They asked, okay, how much money do you need? How much CPU time, memory, IO do you actually need? And the funny thing was that I couldn't answer that. It was just not answerable, because I don't know what kind of model they're going to be using. I know the data that I have. It's at this point it was 100 million videos. So how do we actually know? How do we budget this? Right? It's a very simple question, and Google and other state-of-the-art players seem to say more data is always better, and also more compute is always better. And as I said before, more parameters are always better. And I was like, there's something not right here. It's better if you obviously spend more money on compute for them, but how does it really work? So in order to get there, let's play a game. Here I'm giving you a very simple sequence of numbers: 2, 4, 6, 8. What's the next in the sequence? And most people would answer 10, right? So why is it 10? Well, because when I look at those numbers, it turns out these are all even numbers. So that's the rule, or you could say plus 2, okay? Now I'm giving you a different sequence: 6, 5, 1, 3. Now what's the next number? And it turns out that's not such an easy question. In fact, we deliberately chose that to be unanswerable, because 6513 is the last 4 digits of my phone number. And my phone numbers are, unless you pay for 1-800 number, completely random. And so since it's a completely random sequence, turns out there is no rule to extract. 6513, all I can do is memorize 6513 and think about it and hope maybe I get more data. And so this is interesting, because right there we have a notion that when we have 2, 4, 6, 8, and we can say 10, 12, 14, 16, and so on, if I ask for the first sequence 1000, what's the next number? Because you know the rule plus 2, for this unseen data 1000, you can already say, oh yeah, it's 1002. While when for the second sequence 6513, I ask for what's the next number, it'll be, I don't know, because all I could do is memorize 6513, but I'm still figuring out what's going on. While 2468, it doesn't even matter to me anymore that it was 2468 how I learned it. If you have the rule +2 in mind, you can take any number and add +2 and you're good. So you generalize this rule to actually an infinite amount of numbers. By 6513, you can't do anything. Yes, so that actually is the conceptual idea behind Brainome, okay? The conceptual idea is if you give me a bunch of data, I can always build a classifier with 100% accuracy, which is a dictionary, okay? Take the input data and store it verbatim and map it to the output, okay? So you can take all the cats and dog images, save them, and if you have that exact cat and dog image again, obviously you match it and you say it's a cat or a dog. So memorization is the simplest way of prediction, but it has a problem because now we actually can only look it up. It's also called lookup table. And that means, for example, 6513, I can memorize. I can always memorize, but I couldn't deduce a rule. And so memorization is basically like overfitting. It's just worst case generalization. There's no generalization, in fact. All you can do is you can be lucky that you find the exact same sample again when you have it in your validation set. But what we really want is we want to generalize. And generalize means that even if I don't find the exact same sample, so if it's a cat with noise or a dog with noise that has not been in the training set or not even in the validation set, I still can say it's a cat or a dog because there was some inherent rule that the machine learner extracted, just like +2. And that actually is the main idea, but there's also an engineering assumption in here in Brainome. So now, how do we know that our machine learner actually can extract a rule versus not extract a rule before we train? And the interesting part here is that we can do so because what we will assume is that the smallest amount of parameters in your model will give you the best generalization. And it's actually not just an assumption, this can be shown. Now, there could be generalization even with a lot of parameters, but we will just disregard the case because we will say as engineers, we want to build a car with 4 wheels and not 25 wheels, okay? The 4-wheel car is the most general car, so let's build that. Of course, there could be a 25-wheel car that also works, but really the standard case is we want the smallest amount of parameters, and that means that each parameter has to obviously, compared to the lookup table, take up a lot more predictions than one. And that means there's a high chance that an unseen prediction can also be done correctly. And that's sort of, again, there's the Cortex 201 where I can go into the math of this, but this is the major trick. And now we can go and measure data sets. You know, when we looked at 246810 and 6513, there was just the data set. We didn't even consider any specific machine learner. But what we can do is we can also know the specific properties of these machine learners. And we know that from, well, that's basically the work that Brainome did. And so we know for neural networks and decision trees, for example, we already have that in our product. We can show you how many parameters something would need before we actually even build a model. And so that product is our main product. It's called Dimensions, Brainome Dimensions. Brainome Dimensions gives you a lot of other measurements as well that are sort of based on the same notion that memorization is worst case. And so again, the first thing is to figure out, do I need a decision tree? Do I need a neural network? And of course, this is in the future to be extended to other machine learners as well. The second thing is, do I have enough data? So do I have enough data is, for example, is the same analogy. So 2, 4, 6, 8, 10, you have enough data. If I gave you 12, 14, 16, 18, 20, 22, and so on, at some point you just tell me to stop. You just say, I have enough data. I know the rule is +2. Why are you bombarding me with data? Which, by the way, right there contradicts Google's assumption that there's no data like more data. There's actually no data like enough data to finally find the rule, and this can be measured. And so the way we do this, and I will show you in a bit, is that we go and say, okay, let's take the training set, let's take 10%, 20%, 40%, and so on of the training set. And if it turns out the ideal machine learner wouldn't need to add any parameters anymore, congratulations, we actually found a rule. But if it's linearly increasing, then yeah, like 6513, all you can do is whenever there's another number added, you need another parameter to store it, right? So that would be basically the point that you can make if how much do you have enough data. And then we can, based on those, find out about a generalization ratio, which is nothing else but the number of correctly classified instances divided by the number of parameters, or divided by what we call the memory equivalent capacity. Again, in the 201, we will go into depth on this. And then also we can detect overfit, because we know when a neural network is actually memorizing, or decision tree is actually memorizing, or even using more parameters than needed for memorizing, compared to when it's absolutely has no chance to memorize because there's very few parameters compared to what it would take to look the data up. So why are you interested in this? Well, because that actually gives you a bunch of benefits, especially for data preparation, right? So first of all, before even going and guessing what model you need, the first question is, do we have enough data, right? So we can tell you that. We can give you, basically, we give you like a traffic light, green, yellow, red. Then know when you have the right features. So the point is, sometimes you have these features and you take it out, and it turns out then the machine learner actually could generalize. Now, in today's state of the art, you have to actually train a model for that to figure this out. But no, we can tell you a priori whether you're adding those features or not will actually make it more or less generalizable. We know when we're overfitting. We will clearly tell you this is overfitting, but you'll also see that overfitting is nothing completely Boolean, okay? It's not yes, no overfitting. Overfitting is basically, we don't overfit when we have a rule, or we overfit when we have to memorize. But in between could be a rule with a bunch of exceptions. And as we know, there's no rule without exceptions. The question now is, in the trade-off between accuracy and generalization, where do you want to be? And we give you that choice. And then also now know the rules, know what the rules are that you learned. So we tested our stuff on 180 OpenML tasks, to be frank, 176, totally through the bank: financial data, audio, computer vision, NLP, speech, biology, all of these. And what interesting is that in 100% of the cases, our models are 2 orders of magnitude smaller. We train 2 orders of magnitude faster. And by the way, in 85% of the cases, we beat the state of the art. And this is all without any tuning, all based on measurements. And the interesting part, though, is that now that you have models that are 2 orders of magnitude, basically a factor of 100 smaller than typical models that are currently in the market, you open them up and you see, oh yeah, it's just a bunch of simple rules. And in some cases, it's sometimes just one if then, right? And it's a complicated if then, but it's one. And of course, that is very interesting to see when you just derive a simple rule. So it adds a lot to the explainability. And the other thing is that's kind of interesting, because people talk to us about, is data drifts. So obviously, if you have a certain number of parameters that you need for your neural network or for your decision tree, and you build that decision tree, and for some reason this goes up suddenly, well, then you know something changed in the data. So that's important to detect data drift. And then you probably have to rebuild the model or do changes or see what's going on. And that's very nice to be able to see that basically in real time, because we take no time to do these measurements. Yeah, and again, in this webinar, I can't go too deep. It's just a sort of an overview of what we can do, but also I will show you how we do it and basically how it works. So I'm gonna just share my screen, and I'm gonna show you what even you can do at home. So this is our website, brainome.ai. And the most interesting part for me, apart from a bunch of videos that explain a lot more than I can explain right now, is you go and just try the demo. Okay. When you try the demo, it shows you right away there's this process. You upload your data, you measure it, you build the model, you predict. Okay. And so I'm going to use one of the examples that we put in there, which is a banknote. So banknote was a task in the 1990s. It's actually still an active OpenML task about forgery detection. So there's like 3 wavelet features, just computer vision features. And then the question is the banknote fake or is it a real euro note? And so the first thing I do with this data set is I just measure. Okay, so I have this data set now and I know nothing except what I just told you. So the typical way to go with Brainome is to just go and measure. So now I measured it. Now I can go deeper and see what's going on with this data. First of all, yeah, it's 1372 instances and 4 attributes in 2 classes, forgery or not. And if I did nothing and just guessed the majority class, it would be 55% accuracy. So it's not completely balanced, but mostly balanced. And now the next thing we do is we ask, okay, what's the learnability? So if I learned this with a neural network or if I learned this with a decision tree, how many parameters would that need? And it turns out, yeah, if I learned this with a neural network, it would take about 37 parameters. And if I learned this with a decision tree, it would take about 43 parameters. Which then, assuming 100% accuracy, gives you 2 generalization ratios. Here would be 37 bits of prediction can be stored. Bits of prediction can be stored in 1 parameter, and here also 31 bits of prediction can be stored in 1 parameter. So overall, neural networks seems to be better for those. But there's other metrics. So the second other metric is the capacity progression. The thing that I said before, that there's not like there's more data, no data like more data, but there's no data than enough data to infer the rule. And so we see for an ideal machine learner, can we infer the rule? And it turns out in this particular case, so if this goes like this, like linearly, sort of, slicing diagonally through this graph, that would be very bad. That would be, we can only memorize. But if it went up like this and stayed straight, that would be what we actually want to see. And now I intentionally show you this data set because measurements are measurements. So, and nature is nature. So in this case, what happens is that we actually, it looks like actually it converges. And then unfortunately, oops, it doesn't completely converge, which makes the system give us the recommendation of, maybe it'll work, but unfortunately you got to try. Okay. It's a yellow, it's kind of in between. And since we know this, that there's probably some memorization that has to be going on, we can look at overfit risk. And it actually tells us, with a neural network, you might actually overfit quite a bit. Better try a decision tree. Okay, well, that's what we're going to do then. So we go here and say, let's build a decision tree. And it predicts the build time, which is less than a minute. So it's going to be about 20 seconds or something while I'm talking. It's building right now. So it's training, splitting and training and validation set, and training the predictor on this bank task. Okay, it's done as I've done it right here. And now we have a best guess of 55.53, but we improve over that by 43.52%. So we get a total model accuracy of 99.05. That is something like 1 or 2 instances incorrectly predicted. Everything else is correct. In fact, we can actually look this. This is actually wrong. This is 8 plus 5. This is the confusion matrix. So class 1 is chosen 757 times correctly. Class 2 is chosen 602 times correctly. And then class 2 is classified as class 1 8 times, and class 1 is classified as class 2 2 times. So in fact, 13 instances incorrect, okay? But overall, I've got pretty good accuracy, and the model capacity ends up being smaller than predicted. This is actually what we aim for. When we say that there's going to be 43, then this is what's going to happen or less. Okay, so this is an upper limit for what's actually going to happen. And the nice thing is, since we have only 29 parameters, that means we have a nice generalization already of 46 or 47 or so to 1, which means each parameter can predict 47 instances. So that's a pretty good general model, which then means we should probably either just validate with a completely external data set, or upload data to actually productively predict. Or if you sign up for free here, you can actually download the predictor as a self-contained Python program that really only needs Python 3 and NumPy, and it'll just do whatever prediction you want, and you can modify it, and you can just do whatever you want with it, and you're done. Okay, so that's basically how we do machine learning. And I think I'm just going to go back to the slides, but open it for question at this point.
We do have a few questions, Gerald.
Okay.
Maybe I could feed them to you. Abe would like to know, what are the requirements that you guys have for data input? How big can the data set be? Are there any kind of limitations that he should be concerned about?
So in general, no, but of course, then there is some, commercial limitations. So for the demo file, we say up to 25 features. I mean, this is sort of the demo restriction. And then also, if you sign up, you get better. If you sign up for free, you get more. And then obviously, if you talk to us and we figure something out, then there's no more restrictions. And I want to say though, in general, we are actually really good with files that other people can process. So a typical thing where we work really well is when you have a lot of features, but not so many instances. This is, for example, in genomics, often the case where you have the entire human genome as gene expressions, 21,000, but only, let's say, 600 patients. And then usually other methods just overfit because what do you do with that? So what we do is we will select the right ones and automatically work with those. That's actually another talk that we give. But I was going to say, if you have odd size files, talk to us.
Great, good answer. Looks like Abe is happy with that answer.
Okay.
So let's see. Oh, here's a good one from Corey. Corey wants to know, what do you mean by parameter count? He says, it seems like you think fewer parameters is better. Why are you saying that?
Well, there's a couple explanations for this. First of all, if you just want philosophy, then it's Occam's razor, right? The smallest.
I think maybe starting with what do you mean by parameter count?
Oh, parameter
Might
count.
be a good
So
starting point.
that
Yeah.
is the number of variables in the model. Okay, so you have to train a model, right? So training means we change those variables. And of course, that means the fewer variables I have to change, the faster the training will be. That's the first implication. But the second thing is that these variables sort of explain the data. And Occam's razor, just starting with philosophy, says this, the fewer, the smallest explanation that is correct is actually the favorable explanation. And that was obviously, Friar Occam, someone in the 1700s. But we also know now that, first of all, it's an engineering principle. You want the fewest parts that work. And that means also the least parts that can break. But also the third one is that we can now show, and this would be again in the next talk, that if you do that, you can really mathematically show that the fewer parameters, the more generalization. You can literally sort of estimate your validation accuracy based on the number of parameters you have.
Very interesting. And by the way, what Gerald means when he says the next talk is Cortec 201, which is being presented next Monday at 10 a.m. Pacific. All of these webinars are recorded though, so if you can't make that time slot, you can always watch the video later. I'm going to encourage everyone to put some more questions into the Q&A window. I do have 2 more here, and we do have time for those. And we'll also have time for more questions if people want to add questions. So let's answer Sandra's next question. Maybe an interesting question for you, Gerald. She says, if this measurement approach is so strong and useful, then why haven't Google or Amazon or others done it yet?
Because they have a different business model. Their business model is to sell you compute time and to keep you in their cloud as long as they can. Our business model is we have a software that we license, and we want you to use it as many times and as productively as you can. So that ultimately is the difference.
Interesting. Oh, and Melinda would like to know, what does the percentage mean when you showed the risk of overfit? Maybe we could go back to that slide, Gerald.
Okay, so
take a look at that. What does that percentage actually mean?
New share, give me a sec. Sorry, new share. Here we go. This percentage, right? Oops. Yeah. So this just means. So here's what's interesting. In a neural network, just think about this way. If we're having a very small neural network, that's kind of cool. But what if we took the neural network and said, no, I want to force 100% accuracy. Okay, so I want it to be 100% accurate. then you would have to do a lot of compromises, because what we want is the neural network or the decision tree to find the rule. But if that rule is only 80% correct, and you kind of need for your business case, you just need higher accuracy, and you're okay to sacrifice some of the generalization for that. Then I would like to know, so how bad is that? And what this does is it looks at this and says, okay, assuming 100% accuracy, what's the risk that we are overfitting here? Okay. And so neural network is inherently higher, because if you need to add more parameters, you can't do parameter by parameter. You usually have to add an entire neuron, which then also implies another connection to an output neuron at the minimum. So, and depending on the number of attributes you have, an entire neuron adds a bunch of parameters plus the connection. And that means that in the end, you turn out to be at a much higher risk of overfitting if you wanted to force it to 100%, than in this case with a decision tree. That's what this is. So it's basically saying, forcing it to 100%, how bad would it be? And so now in both cases here, 6% and 60.66%, we're fine. Okay, this number is that you see all this green for a long time. It's really just bad if you're close to 100. So the neural network risk is inherently higher, but once you get close to 100, you should probably avoid it. However, I do like the decision tree here because it was fast, and if I used the neural network, it would take a little longer to build, and so I had to talk a lot longer before we get a result. Okay. But apart from that, that's the idea. So what is the risk that you have to overfit? And it's actually explaining here for 100%.
Great. Thank you. That was super helpful. There is a question in the Q&A from Anurag. Anurag, I'm asking you to unmute because I don't think I could do your question justice, and I'd like you to maybe
Sure.
talk with us about what your question is.
Sure. Hi, Gerald. Yeah. So I wanted to ask how can we upload NLP-related data onto the platform, since we are working with text and that may be converted into vectors, but when we are building sequence to sequence models, so how would the platform benefit and how can we get the measurements in those kind of scenarios?
Yeah, so first of all, you should use the measurement to guide you for this, but I get that's a bootstrapping problem right now. But so the way I usually go for NLP tasks, first of all NLP tasks are different. I mean, are you doing retrieval? Are you doing translation? What are you doing?
So we are doing sequence to sequence model for predicting the best way forward for the user in a conversational bot scenario.
So that is actually very similar to retrieval task. So what you would do there is I would do is I would sort of extract some kind of topic signature or some kind of stuff to just get rid of stop words and all of these. I would create some features out of this, and ultimately you need to model it as a classification problem, right? So you would have, if you have responses that come out of the chatbot, what you would do is you would go and say, well, okay, I have this set of responses, which response is the best here, right? And so you would start to annotate that, the sort of the signature as the input and the response, as a class as the output. Yeah, and then you can measure learnability and all of this, and sort of play around with this before you go and try to model it. Does it make sense? Because I don't know enough about the task.
Anurag, maybe I could just put the invitation out there that we could work together offline and do some experiments together. We're very open to that.
Sure. That would be helpful.
Great.
Yeah.
Are there any other questions? Your questions have been very good today, team. So Gerald, I think we can probably roll on back to the conclusion here.
Yeah, here we go. And then
wonderful. So Gerald just presented Cortec 101, which was a conceptual overview. I'm sure many of you are eager to understand, well, what's really going on here? How are you able to do this brand new approach to measurement? So come back for Cortec 201 and see all the math, see the algorithms, see how it works in detail. And also come back for Core Tech 301 to see a bunch of examples, to see how it all unfolds when you actually put it into practice. You're also more than welcome to come on Thursday for how to superpower your data preparation. And there's a whole sequence of 5 other benefits and applications webinars that are coming on Thursdays between now and the end of the year as well. Also, we really encourage you to just jump on over to the website and sign up and use the software. You can use it without giving us any information as a demo, or if you become a registered user, you can get a free account that has a couple of additional capabilities associated with it. We just love to get to know you, and you can always email support@brainome.ai with any questions you have, and we'd love to help you figure out how to solve your problems, just like we talked about with Anurag. So there's one more question in the Q&A box. Let me see. Oh, that doesn't look like it's going to pan out. Well, thank you very much, everyone, for joining us today. We hope to see you next week for Core Tech 201 or at any of the benefits and applications webinars that are coming up on Thursdays for the rest of 2020. Thanks all. It was great to see you here.
Yeah, thank you so much for listening. And yeah, we are open to questions, obviously, and there's a contact portal. And I really want to encourage you to just try it out and get inspired by this. Thank you so much.
Bye, everybody.